Okay, we're going to take some notes today. So the first thing you want to do is go into Canvas and go into our Kinematics module and get document 05. So if you get document 05, that's Kinematic Notes. When you open that up and put it into Notability, it should look just like this. So go ahead and pause this video until you've got document 05. All right, we've been talking about a couple different things that we've been measuring. When we went outside, we measured distance walked and time. We talked about calculating speed and looking at the graph. So we're going to start defining this and making sure that we're kind of all on the same page with the terminology that we are using and with some variables that we're going to use as well. So the first thing we're going to talk about is position. And position is simply location measured from an origin. So for instance, when we were outside and we were measuring, we always put our tape measure or our rolly wheel at the beginning, right? And so that would be our origin. We're going to use the letter X to stand for position, and our standard units are going to be meters. So I know some of you use centimeters, some of you use feet or inches or other things, but our standard units are the units we're normally going to use are going to be meters. Now be very careful, because some people in their graphing, they put meters on the y-axis, which is not really correct, because we are always going to put on our axes, we're always going to label our axis with the name of what we're graphing. So you could have done position, oops, I didn't want that to be the highlighter, sorry about that. So you could put the name, position, or you could put the variable. We will still always put the units, but you don't want to just have meters being the name, okay? Because meters is not something we measure, it's a unit we measure something with, okay? All right, then time obviously is easy. I don't think I need to define time. We are going to use lowercase letter t to stand for time. It's got to be lowercase. Uppercase t means something else. And we're going to measure time in seconds. Those are going to be our normal units. You can always just put SEC or just the letter S for seconds, okay? Speed is going to be the rate at which distance changes with respect to time. So WRT is with respect to time. We're going to use the letter S to stand for speed, and we're going to use meters per second to measure speed, okay? Velocity is very similar. I'm going to use the term velocity and speed kind of interchangeably, especially for now. And velocity is simply the rate at which position changes with respect to time. And we're going to use the same units, meters per second, to measure velocity. Another way to look at speed and velocity is that speed, and I don't know where to put this, but I'll put this here, speed is basically the absolute value of velocity. So speed is never negative. Let's talk about magnitude and direction, and I'll change color just so that it's a little easier to see, okay? So magnitude simply means how big something is, or its size. So we need a number, right? And we always want to include units with that number as well. Direction is right or left, maybe, up or down, backwards or forwards, north, south, east, west. Okay. So we will, for the most part for right now, since we're just looking at things moving in one dimension, for instance, right, left, and not combined with up, down, we're going to not worry too much about the direction. We are going to mostly talk about magnitude. Okay, size. We might have a negative number thrown in there to indicate that positive is forward, negative is backwards, but for the most part, we're not going to have to worry about direction very much for right now, okay? Now, we collected a bunch of data, all right, and we talked about some methods for collecting position and time data, and we came up with two different methods, right? So we can collect positions or position data at chosen times. So time, in this case, would be our independent variable, right? Or we can collect, I'm realizing this document should have been much larger, we can collect time data at given positions. So those are two different methods that we use for getting position and time data. Just depends on the independent versus the dependent variable, what we're choosing there, okay? We talked a lot about graphing, so we've made several graphs by now. And we know the key parts of the graph. So hopefully you've taken a look at your scores, and we'll do that soon. But we know we're always going to need a title with your name. And it's always whatever is on the Y versus whatever is on the X. We know we always need to change our axis name, right? So we're not going to just leave it as Y and X. It's going to be position, or it's going to be time, or it's going to be X, or it's going to be T. So we always need to change the name of our axis, and we always need to include units with that. Okay. We always need the points of data, obviously. We always need a line of best fit. And we want to pick some simple lines of best fit, okay, proportional. I don't think too many people use proportional, but it's actually the simplest. Linear, inverse, and squared are pretty much the only ones we are ever going to use. Okay. And by squared, I think it's actually on the app, it's called quadratic, so that's fine, okay? Now, that's just kind of some housekeeping, some documentation. Here's where it gets interesting, all right? Because a big question that we're going to ask is, how do we know if velocity, and by velocity I could also say speed, how do we know if velocity or speed are constant? Well, think about this. We know that your speed, for instance, when you came here, maybe in a car today, you measured your speed in miles per hour, which is just a distance divided by a time. So if I look at this graph right here, I can see that I've got position over time. Position is similar to distance. So I can see that the slope of this graph is going to actually give me velocity, because the slope of this graph is going to be in units of meters per second. Meters distance times seconds, very similar to miles per hour. So velocity, let me make sure I've got my pen here. Velocity is actually given by the slope of a position graph. So if the slope is constant, it means I'm going at a constant speed. Okay, so constant slope means constant velocity or speed. Well, by looking at this graph, how do I know that the slope is constant? Well, it's a straight line. Anytime I have a straight line on a position graph, I have a constant slope. Now, maybe the line is a little bit different, right? Maybe the line looks like this. Maybe the line looks like this. And sorry, I'm trying to draw straight lines. The app I'm using isn't as good as Notability. So in both those cases, I would still have a constant speed. If I saw a curving line, you guys in your math class have probably seen a line like that. This curving line does not have a constant slope. Therefore, I know any object that created that kind of line would not be a constant speed, okay? Now, if you remember from math class, you know that slope can be found by taking the rise over the run. In our case, the slope would just be a change in position over a change in time. Boy, writing change in is sure a problem, so I'm going to use what we call a delta. Look at that that's a little triangle. That stands for delta. And delta means change in. So the slope, I can write the slope as the change in position, and since x means position, I can just put x over change in time, okay? Okay, on to the next page. What are the units for this graph's slope? Well, we just said that slope was velocity, and it's change in position over change in time. Well, we measured position for that graph in meters, and we measured time in seconds. So the units for the slope are meters per second. Sounds very similar to miles per hour. There's our velocity. So anytime we want to calculate the velocity of an object from a position time graph, we just calculate the slope. Pretty easy, okay? Now, what's the difference between velocity and speed? Like I said, I'm basically going to use those interchangeably, but velocity is just speed in a direction. Okay. We normally assume that a positive velocity is either up or forward or to the right. We generally assume that a negative velocity is down, backwards, or to the left. That's just a convention. We don't have to use that convention, but it's what we will normally do in this class. We're going to use dot diagrams to kind of convey information about an object that's moving. So we can see here, we can see this dot diagram here, and I would look at the spacing for these dots, and I would say, okay, this spacing from this dot to this dot, this spacing from this dot to this dot, this spacing from this dot to this dot, they all look pretty similar. So I would be pretty confident in saying that the object that created this dot spacing for this dot diagram was moving at a constant speed. If I saw another dot diagram, which I have down here, look at how the spacing has changed. And let's say that these dots were made every 0.1 second. So let's go up here and say this dot was made at a time of 0 seconds. This dot was made at 1 second. This one was 2 seconds. This one was 3 seconds. This one was 4 seconds. Okay. So the space between the dots shows the change in position. So the space is the change in position. And then let's look here, okay, and we can say, okay, this dot was made at t equals 0, this was 1 second, this was 2 seconds, this was 3 seconds. Look at how the distance covered in that same time interval has decreased. So the distance covered in the time interval, which we can call delta t, I'll make a better delta t, has decreased. So think about which of the two objects, the object in this first dot diagram or the object in the second dot diagram, which one do you think was moving faster? Well, if you cover more distance in the same amount of time, that means you're going pretty quick. So this object that made this dot diagram is going to be going faster. This one right here is going slower. So it covered less distance in the same delta t or same time interval. Put in positive slope, don't know how that happened. So there are a lot of different ways to convey information on position and time. One of those ways you did in the lab that we finished, you created a data table where you listed in one column you put position, in another column you put time. And that's a great way to collect data. It's not the best way to portray data or show data to someone else, because you have to really think about what's happening with each of those data points. A better way is to use graphs. So that's why we had you create a graph of your data using graphical analysis. Because you've heard the saying, a picture is worth 1,000 words. The graph is basically the picture. So we're going to have to get used to reading graphs and understanding what those graphs are telling us. And this is a great skill to have in science in general, and a skill that they're going to actually test on the SAT when you take the SAT, and if you take the ACT as well. So we're going to talk a little bit about these different graphs, and we're going to see if we can figure out what each graph is portraying. So let's take a look at this first, let's go with first row, where we've got an object at rest. Okay, so we've got an object at rest in this first one, and we're going to say the object is right at the 0 mark. So if you're a football fan, this could be like the line of scrimmage. You can think of it as the lab. We're starting at where we've got our tape measure starting at. You can think of it as starting at your home base. Okay, so we've got an object that's at rest over the entire time period and is starting at a 0 location. What would that graph look like? So since the person, and let's assume a person is moving, the person's not moving, we're going to have a horizontal graph right at the origin. That's it. We could go ahead and we could put in, we can label these graphs. So this would be X, and we could put centimeters, and this would be time in seconds. And that's it. That's all we would see. So now in this next one, let's assume that you're getting a head start, right? So you're not starting at the line of scrimmage, you're starting ahead. Still at rest. What would that look like? That's going to look like this right there. And I can go ahead, I can make that a little thicker so it's a little easier to see. It's going to look like that right there. Okay, so we're kind of starting in the positive X direction, okay? And then if we're starting behind, we're in the negative area right there. And then again, we can go ahead and we can label this, so we could put X and T, and we'll just put X and T. We won't worry about the units right now. And we can go ahead and do this for all the graphs right now. Should we have done that for you? Yeah, probably, but you don't mind doing it, do you? There we go. And we'll just get these all done right now, okay? So at rest, if an object's at rest, we know we're going to see a horizontal line for the position graph, okay? Now let's go ahead and let's take a look at what we're going to see if an object is moving forward. This is exactly what we saw in your lab. We saw a straight line position graph with an increasing slope. So again, let's make that just a little thicker. It's going to look like that. It's still a straight line, okay? It's still a straight line. It just has a non-zero slope. Up here, right, we would call this, and let me go ahead and change the color and change what it looks like so we can write this out. This is a 0 slope for all of these, right? This is 0 slope. And this is still a 0 slope. When we talk about moving forward, we have a positive slope. And we're going to find that's going to be true for our other graphs as well. So I'm just going to go ahead. Positive slope there and positive slope here. Now the line is going to look a little bit different because it's going to start someplace else. It's still going to be a straight line. It's still going to have a positive slope. But if I'm starting, if I have a head start, I'm going to start up here. And if I'm starting from behind, right, I'm behind the line of scrimmage, that means I'm starting here. I'm still got the same straight line. It's just offset a little bit. Basically, if you're a fan of equations in math class, it's got a different intercept value. It's got a different b value, okay? All right, let's take a look at what it means to be moving backwards. So if we're moving backwards, we're still moving at a constant velocity. We're just going in the opposite direction. So now it's going to look a little bit different, and we're going to be going still constant velocity, still straight line, just going down. If we are starting ahead, right, we're still starting ahead, we would be starting from up here. And if we're starting from behind, we would be starting from down there. So the biggest difference here is that now, instead of a positive slope, we have a negative slope for each of these situations. So if you have a negative slope, you know that the object is moving negative direction, meaning either backwards or maybe down or something like that. So let's get some practice with graphing, and let's go ahead and let's draw just some simple graphs. So I'm going to draw a very simple, and you can straighten these lines out. The app I'm using doesn't. I'm going to draw a very simple position graph, and I'm going to go ahead and I'm going to say, okay, if I've got my dog sitting on the floor and not moving for 1 minute, what is that going to look like? Well, since there's no motion, I know I'm going to have a horizontal line. I'm not given any information for where the dog actually is in relation to an origin. I haven't even chosen an origin. So I'm just going to say, well, there it is. There's the dog sitting still on the floor for 1 minute. I'm just sketching it, so I'm not going to label any values anywhere. We can keep going, and let's try another example, and let's go ahead and draw our axes. And if you want to draw them and then kind of copy and paste them down, you can. So here's our position. Here's our time. I'm going to go ahead and do that for a couple of them. Oops. Okay, that's not working. There we go. Position and time. I'm not very good at drawing straight lines. And then we'll go for this one as well. I'm going to have to change it up a little bit for this one, for number 5, because I think I'm going to be going in the negative direction a little bit more. So I'm going to go ahead and do that. Okay. All right, so let's go back up to number 2. And this time, your brother is walking across the room at a constant velocity for 10 seconds, and then sitting on a chair for 10 seconds. So what is that going to look like? So this is kind of a combination of what we've seen before. So if he's walking across the room at a constant speed for 10 seconds, we know we're going to have a straight line with a positive slope. And then if he's sitting on a chair for 10 seconds, he's not moving, so we know that he is going to be going nowhere. So he's going to have a horizontal position graph. That's it. That's what it looks like if your brother's walking across the room at a constant speed for 10 seconds and then sitting down. Let's take a look at what your sister is doing here. Okay, your sister's walking across the room from her desk to the kitchen table at a constant velocity for 10 seconds. So we'll call that going in the positive direction. So there we go, moving in a positive direction for 10 seconds. She then sits on the chair just like the brother did for 10 seconds. So here's another 10 seconds of not moving. But then she returns to her desk. So she's not technically, she's not facing backwards when she's walking, but she's certainly moving in the opposite direction from when she walked to the kitchen. So we have to have her moving in a backwards direction. So she's going to have a negative slope. So that would be her position graph for moving first towards something, standing still, and then moving back where she originally started. All right, try a couple more. Now we're going to sketch a graph. We're going to walk in a straight line for 20 seconds down the sidewalk to the corner. We're going to stop for 15 seconds. Then we're going to turn around and go backwards, but we're going to pass where we originally started from. We're going to go to a different neighbor's house. So I'm going to go ahead and I'm going to erase this right here. And I'm going to go ahead then, and I'm going to move that up a little bit. So I want my time axis like this. So let's see what that looks like. Okay. So you walk in a straight line for 20 seconds. There we go. I'm walking at a constant speed for 20 seconds. I get to the corner. I stop at the corner for 15 seconds. There we go. I've saved stop for 15 seconds. Then I turn around, I go backwards. I get to my house, which is at the axis here, but I go past it. And that's not a very good straight line. So let's see if I can fix that up a little bit. Looks like that. Okay? So I could label, if I wanted to, I could label some times here, right? This would be time 1, this would be time 2, this would be the first 20 seconds, and then, so this would be like 20 seconds here, and then 15 seconds of standing still. I could put 35 seconds here. I don't always have to do that, but if you want to put that in, if it helps you understand what's going on, that would be fine, okay? One more example. So we've got a running back, so football started. Okay, so we're going to sketch a graph. The running back starts 5 yards behind the line of scrimmage. That means I'm going to have them start somewhere down here. Okay. She runs forward for 5 seconds. So it doesn't really give me much information for how far she gets, but I'm going to assume she gets past the line of scrimmage. So we're going to go at a straight line like that. But then a big scary linebacker chases her back for a 10-yard loss. Okay. So if she started 5 yards behind the line of scrimmage, that means if she loses 10 yards, she's really far back. So she started 5 yards behind the line of scrimmage. So she is 10 yards now behind the line of scrimmage. So I've got to have something that looks like that. We're using straight lines. Now, we've made an assumption here, and it's not a great assumption. We've assumed that she's always going at a constant speed. Well, how can that be if she's turning around and going backwards? Clearly, she couldn't be going at a constant speed while she's turning around. But for right now, we're going to ignore that little bit of time where she had to turn around and change her speed, and we're just going to use these straight lines. In the next unit, we're going to talk about something called acceleration, and then we're going to worry about speeding up and slowing down and how that works and how you can't just change direction on a dime. But for right now, we're just going to let it be, okay? So that's it. Those are our examples. You are ready to try some on your own now. So you've got a couple of worksheets that you're going to work on. So I'm going to stop the video here and let you guys get to work. Thanks for watching.